The adjoint methods are a particularly efficient way of obtaining gradient through implicitly given relations. So for instance, linear systems. In this video, we want to implement the adjoint method together with the forward sensitivities and the finite differences in Python, and then compare their results as well as their timings, so that if you run them, you see the comparison of gradients and the timing it takes for the methods to achieve their results. So let's get started. Hi and welcome to this new video. The agenda is that we will first recap on what sensitivities of a linear system are, then we will discuss again the three major methods to calculate them, namely finite differences, forward sensitivity analysis, and backward or adjoint sensitivity analysis. Afterwards, we will implement all of them in a simple example in Python. You can directly jump to the coding section by using the chapters of the video. Now let's get started with our quick recap. We are looking at linear systems of equations. That means we have a system matrix A multiplied with a vector x equals a vector b, and our task is to find the vector x that satisfies this equation. This is a typical problem in numerical analysis, and there are many algorithms to solve for this x. Let's assume we have a suitable algorithm that solves and yields an x here. Now we have the solution to this linear system, and then we plug this into a loss function. This loss function can be of multiple kinds, but quite common is something that is comparing the solution that we got with a reference solution. So let's say we have a reference solution. So the solution, let's call it xr. This also enters the loss function, and then we create what's called a quadratic loss. So we say j is x minus the reference solution transposed times x minus the reference solution. And here you see vector minus vector is a vector, and then if you transpose a vector and matrix multiply with the original vector, then you essentially have the scalar product. So this also contracts the dimension that we have here into the scalar. And we usually add here a 1/2, which will make sense later. And what is a potential physical interpretation of this? For this, let us look at finite element methods, where you get usually large, sparse, linear systems. And the unknown x is usually u, the displacement of the points in the mesh. And if you solve for this, then you know how the points are displaced. And then you might have a reference solution, because you did the same experiment in real life and also measured the displacements there. And now you want to compare how close your finite element solution is to the real world solution. So the smaller the loss value, the closer you are to the real world solution, the bigger it is, the further you are apart. And what we are now interested in is that the components in our linear system, so the system matrix and the right-hand side, could depend on some parameters. So in the case of finite element methods, this could, for instance, be constitutive parameters. Then they might be entering the system matrix here. But for the sake of simplicity, we will only consider the right-hand side being parameter dependent. So let's say the right-hand side b depends on a parameter vector, theta. For instance, these define what kind of loads we have on the system, so the forces that will displace our structure. And then we might be interested in getting the sensitivities. So the sensitivities are the derivatives of the loss function with respect to the parameter vector, or more precisely the total derivative here. And that's what we're interested in. Because with this gradient information, we could change the right-hand side such that it mimics the right-hand side for the reference solution. So in other words, if we only observe the displacements in real life and we don't know the loads of the structure, we could then use these sensitivities in an optimization process to find the right-hand side that is better than our initial guess that we used for a first solution. Now let me make this a little bit more concrete. So I will say here, for the sake of our example, let us introduce some specific matrices and vectors. So we say that the matrix A is fixed, so this one is not parameter dependent. And let's, for instance, make it a 3x3 dimensional square matrix that has the following entries: 10, 2, 1, 2, 5, 1, 1, 1, 3. And we have a right-hand side, b, which is variable, or you can also call it parameter dependent. Let me also put this here. It is parameter dependent. And this right-hand side looks as following. So we have a b, and this must then also be a three-dimensional vector in order to match the shapes of our linear system. And here we say all of the components are unknown. So we have a theta 0, we have a theta 1, and we have a theta 2. But additionally to the fact that those are unknown, we also have a guess. So we also know that, or we think that beta looks as following. Let's call this a beta hat. So our assumption on beta, and let's say it's 1, 1, 1, so a vector just with ones. And now our task is to get these sensitivities, and the first step is of course to get the original x in the first place, where we will just use our b hat to solve the linear system, and then also evaluate the loss metric, and then afterwards we will use our three methods to obtain the sensitivities. So we start with step A, which is to solve the classical problem. And by classical problem, I refer to the original linear system with the current guess that we have for the right-hand side. So what are the steps here? We have step number 1, and for this we will solve the original linear system. So ax equals b hat for x. And we will just use some convenience algorithms in Python, so we don't have to consider particular algorithms to do this. So let me put this in a box. That's our very first step. And then if we have the solution to this linear system, we can evaluate the loss metric. So this will be step 2, where we will evaluate, and the loss metric was given as j is 1/2 times x minus xr in brackets transpose times x minus xr. And maybe let me also make this one yellow here. And then we can also put a box around it. So this is our next step. Now I'm missing the bracket here. And this xr, or the reference solution, is given. And I call it the classical problem because if you would be quite sure about your right-hand side, so if it would also be fixed, you would solve this problem anyways, because this is yielding, in the FEM case, this is yielding the displacements that you are interested in the first place. And now you want to do something additionally. This is to obtain the gradients. Let's call this step 2. So we will obtain the gradients. And by gradients, I refer to the sensitivities of the loss function with respect to the parameters. So dj by d theta in a total sense. And just a quick reminder, in the derivations for the adjoint methods, we assumed that the gradient is a row vector. So we say that here the gradient is a row vector. That's just a convention. It helped us with some multivariate chain rules, but you can of course easily transpose it otherwise if you want to use it for subsequent steps. And now, as mentioned, we have 3 methods to obtain this gradient, and we will go from least efficient to most efficient, and we probably also go from easiest to understand to most complicated to understand. The first option we have, so let's call this the first option, is finite differences. And the finite differences approach is really straightforward. It's not too intrusive in the code. The idea is the following. We say that the gradient, it was a row vector of course, it is composed of the derivatives of j with respect to theta 0, of j with respect to theta 1, of j with respect to theta 2, and if we would have more parameters, it would have been longer. So in our case, just 3 parameters. And then you iterate over all the entries here and calculate them one after the other. So for instance, for the first entry, so for dj by d theta 0, you would do the following. You would create an augmented right-hand side. I will call this b tilde with an underscore because it's still a vector. And this is given as our current guess plus a small epsilon. Usually this is 1 to the minus 6 or 1 to the minus 5. Let me just add this here. This is usually 1e minus 6 or something in that range. And then you multiply that with the unit vector in the 0th direction in that case, because you want to add this negligible amount to the 0th entry in that vector. So if we then go up to our current guess, then the b hat changes to the b tilde, which in the first entry has 1.00001 and then 2 more ones following. So the very first entry, or the 0th entry, is augmented. And then you use the augmented entry to solve the system given as matrix A times x, and I will also call this tilde here, equals b tilde. So use this as your right hand side, and you solve this for x tilde. And now we have another solution, and you can then also evaluate the loss metric. So you will evaluate the loss metric, which will be a j tilde, and here you use the same formula, 1/2 and then x minus xr, or you have to use x tilde, and then transpose times x tilde minus xr. And then in order to obtain the component in the gradient vector, you say that dj by d theta 0 is approximately j tilde minus j divided by epsilon, which was the small amount that we added to our guess of the b vector. This is the most easiest to implement because it uses what you've already implemented. So you have the solving and evaluation routine already in code, and then you can just use them with a different right-hand side. It just takes you more solutions of the same problem. And due to that simplicity, this one is also used to check your gradients. So we will compare the other two methods with this one, because we can be quite sure that if we didn't do any big mistake, that this will be an correct estimation of the gradient. But now speaking of the other methods, the second option we have is to use forward sensitivity analysis. So it will be forward sensitivities. And for the forward sensitivities, we solve an auxiliary system that is given as a times a dx by d theta equals a db by d theta minus dA by d theta times x. And that is like a consequence of what we derived in the earlier videos on the adjoint sensitivities. We then claimed that this is more computationally extensive than using the adjoint method. And that is because here we are not solving for one vector. We're not solving the system for one vector, but we're solving it for an entire matrix. So we are solving a batched system of linear equations, meaning that we want to solve this entire solution Jacobian here. So we want to solve this system for dx by d theta. Although it is a derivative here, you can think of it as an unknown or a temporary value that we want to calculate. But then still we have to evaluate these two total derivatives. And then we would also have an x here. This x is what we would take from our classical solution here, but we will see that we don't need it. So first, let's look at the dB by d theta. So I will say here, and let's start with dB by d theta, which is the Jacobian of our b vector with respect to theta. For this, let's look at how b was defined. And the b was given as theta 0, theta 1, and theta 2. And if we then apply the Jacobian to this, we get the identity matrix. So we are getting a matrix that is 1, 1, 1 on the main diagonal and otherwise 0. And I hope this makes sense. Let me double check it with you, that if you derive theta 0 with respect to theta 0, you get 1. With respect to theta 1, it's 0. Theta 2, it's 0, and so on and so forth. And then let's go down and check on the second total derivative, which is a dA by d theta. And also a quick reminder that technically this is not correct. I probably have to mention that here again. This is not correct, and by not correct I mean it is not matching the shape. So it's the wrong shape, because if you take the gradient of a matrix with respect to a vector, then you will get the three-dimensional tensor, and then these multiplications won't work out as easily. You might need some index notation. But here we see that since we fixed our matrix, so by fixing mean that it doesn't have any dependencies on parameters. If we then take the derivative with respect to the parameters, this will of course be 0. I mean, it's not a scalar 0, it's this three-dimensional tensor 0, but it is 0. So meaning that when we multiply something with it, even if the shapes do not match in this form that I wrote down here, it will still be 0. So this entire component here, the minus dA by d theta times x, will be 0. So with this information, we can then reduce this system and say we solve a times dx by d theta is equal to the identity, and I will use this MATLAB NumPy notation. This means an identity matrix of shape 3 by 3, and we solve this for the solution sensitivities. And we consider them as some sort of like a variable. So this will be the first step in the forward sensitivity analysis. And then we know that we can have our gradient by the following formula. We have dj by d theta is equal to partial j partial theta plus partial j partial x times dx by d theta. And that's why we calculate it here, because then we can plug it in. It requires the solution sensitivities. And then again, let's look at how the derivatives are in our particular case. So the dj by d theta. For this, let us go to our loss function that we have here. And we also see that there is no dependencies on the parameters. So this gradient will be a 0 vector. And in order to match that gradients are row vectors, we say this is 0 transpose. Then we have dj by dx. Then let's execute the derivative. So we have to take the derivative with respect to vector x of the loss expression, which is 1/2 times x minus xr in brackets transpose times x minus xr, and then closing brackets. So we see that we have a product of two factors that both contain the x we are taking the derivative with respect to. So let's apply the product rule. In essence, we're getting 1/2 and then opening bracket of the derivative of x minus xr in brackets transpose with respect to x times x minus xr plus, and then we have x minus xr in brackets transpose times the derivative of x minus xr with respect to x, and then we close this down. Let's look at the last entry first. If we take the derivative of this sum, in essence, with respect to x, we see that this constant addition here does not matter. It will derive to 0, but the derivative of x with respect to x will be the identity matrix. So the derivative of x with respect to x will yield the identity matrix that is of shape 3 by 3 in our particular case here. So this one will be the identity matrix of 3 by 3. And here we have to be a little bit more careful because we have an transposed vector in the numerator, or what the argument of our derivation, meaning that here we have the derivative of something that is of the shape 1 by 3 with respect to 3. So if we take the derivative of a transposed vector with respect to x, we are also getting the identity matrix, but it has the shape 1 by 3 by 3. So it has an additional 1 here. So let's put this down. This is the identity matrix with shape 1 by 3 by 3. And then if we execute the matrix multiplication, we see a vector transpose. This will be a 1 by 3 vector. So this one is 1 by 3. And if we multiply this 1 by 3 with the identity matrix, then this will be also a 1 by 3. So in essence, it will be the row vector. And here we have a quantity which has the shape 3. And then if we multiply these shapes, then we see the last two dimensions kind of cancel, and the overall shape will be 1 by 3, which also matches the shape here, because otherwise the addition wouldn't work. And after this long discussion, we have 1/2, and here we in essence get the x minus xr, but reshaped into an row vector. So we have an x minus xr in brackets transpose plus an x minus xr in brackets transpose, And then we see we have it twice, so then we get it 2 times. So we have 1/2 times 2 times x minus xr in brackets transpose. The 2 and the 2 cancel, and then the solution to this derivative is x minus xr. So then we see, if we go all the way back, that we also now have an expression for dj by dx, and then we can write it down fully so that we have the following expression. We have a then dj by d theta is the 0 transpose. I will just leave it here for completion, plus, and then we have the derivative with respect to x, which was x minus xr, and, or in brackets transpose, of course. Sorry for that. And here also, of course, transpose. And by the way, did you see now why we chose the 1/2? Because this conveniently cancels with the 2 here. It's something that's commonly done in mathematics, because it doesn't change your loss function, but it makes the gradient more nicer. And then we multiply this with the dx by d theta. That was the one from the step before. And then we found the gradient with the forward sensitivity analysis. Now let's look at the last option, which will be the third option. And here we will use the adjoint method or backward method. So we will use adjoint or backward sensitivities. And if you watch the videos, you should be familiar with the solution that we got out there. And it consists of the following steps. So first, we solve the adjoint system, which was A transpose times lambda is equal to dj by dx in brackets transpose. And we solved this for lambda, and lambda was the adjoint variable that we introduced. And now that we've already done this derivative in this previous section on the forward sensitivities, we can just steal the result. It was x minus xr transpose. And if we then transpose it again, we get a column vector. So in essence, what we have to do first is to solve the adjoint system A transpose lambda. And in our case, this derivative transpose evaluates to x minus xr. And we solve this system for lambda. That will be the first step here. And then we can evaluate the sensitivities according to the following formula by saying dj by d theta in a total sense is partial j partial theta plus lambda transpose, and then we have db by d theta in a total sense minus dA by d theta times x. And then we again use the results from the previous section. Here in this case, we know this will be a 3-dimensional zero quantity, so the overall contribution here will be a zero matrix. This one we also know it will be the identity matrix or the I matrix, which is 3-dimensional or 3 by 3-dimensional. And here we also know that this contribution is the zero vector, or more precisely it's zero vector transpose, because we live by the convention that gradients are row vectors. And then by plugging this all together, we get the following to do. So we say then dj by d theta is 0 transpose plus lambda transpose. And here we have the identity matrix. And of course, if you multiply something with the identity matrix, you could have also just not multiplied it with that, but we will keep it here in order to fulfill at least this derivative. Let me also put this into brackets. And with this, we are done with the theoretical part. And now let's start with the coding. Okay, let's get started with the coding part in Python. For this, I have the PDF of the nodes we just did, and I will bring them over once we need them. First step, let's import numpy as np, which we will use for our operations here. And then let's start with a main switch for our file. And with this out of the way, we can then go on. I will first define the system matrix A. We said it will be fixed, so there's no dependency on a parameter. So A will be numpy.array, and then first define our first row, which will be 10, 2, 1, and then the second row, which is 2, 5, 1, and the last row, okay, there's a problem here, so the last row then, which will be 1, 1, 3. Now I said in the derivation that we have access to a reference solution, which I introduced, for instance, by the measurements you have in real life. Here, for the sake of simplicity, let's assume we know for a second the correct right-hand side, and then we use this correct right-hand side to create our reference solution. So I would call this part creating a reference solution. Of course, you should use your reference solution that you have available if this is applicable. For this I came up with the absolutely creative right-hand side. I will say it is the following vector. It is defined as 5, 4, 3. And then we create xref by solving the linear system. And if you're familiar with MATLAB, this is the backward slash operator. In NumPy we do numpy.linearalgebra.solve and then use the system matrix A, and the right-hand side is be true. And from now on, we forget about this be true and just use the reference solution. And first step is to, I will put this in the one here, solve the classical system. For this, we have a guess of the right-hand side, and I will call this b guess. And for this, as said, we will use a vector that is of length 3 but contains only ones. So I will use the numpy ones command. And then we solve the forward problem or the classical problem as x is numpy.linalg.solve, and then we use a and b guess. And then we can also evaluate the loss function. So we will evaluate the loss function, and that's relatively straightforward. We say j is 0.5 or a half times x minus xref in brackets transpose matrix multiplied with x minus xref. And if I bring over the nodes, then we have step A solved. Okay, maybe I will then also call this step A instead of step 1. And bring this over here, and let's call this A. And of course I see here, this should also be an A, not a Y. And now we will start in reverse. Let's first do the adjoint method, since it's probably the one that you're the most interested in. Let's call this our step B, obtaining gradients. And here the first version we use is by the adjoint method. And for this, let me bring over the nodes again, and let's scroll down to the adjoint method. What do we have to do? We have to first solve the linear system or the adjoint linear system, and then use the solution, the lambda, the adjoint variable, and plug it into this expression. Okay, let me leave this up here. And for this, I will again explicitly define all the derivatives, although some of them may be 0. So let's start with the partial derivative of j with respect to theta. So we will say del j, and then I use double underscore and say del theta. So the derivative of our loss function with respect to the parameters. And we see in our loss function, we don't have an explicit dependency on theta. Therefore, this will be 0, and more precisely, the 0 row vector. Therefore, I will use np.zeros and say the shape of my 0 array is 1 by 3. Then we have del j by del x, which will be the partial derivative of j with respect to x. And here we've already seen, based on the derivation, that this is x minus xr in brackets transpose. So I will use x minus x reference in brackets transpose. And here you also see that the adjoint method, and then also later the forward sensitivity method, requires the solution from the classical system. So the thing is, we need to solve it anyways, and then we also require it because this then defines this partial derivative, at least in the particular application we are looking at here. And then we have the db by d theta, which was the total derivative of b by theta. And here we see that this was the identity matrix. This was because our right-hand side just consists of theta 0, theta 1, and theta 2. So we will use numpy.I, and I will just hard code the 3 in here. And let's see if we now have all the derivatives necessary. So we have the dj by dx in partial sense, that's great. We have the dj by d theta in the partial sense, and we have the db by d theta in the total sense. And I will just ignore this here because it would be rather complicated to implement the index notation. And since it will be 0 anyways, let's just leave it like that. Okay, then we solve the adjoint system. So solve adjoint system. And for this, we say that the adjoint variable, this one is the lambda vector, is given as numpy.linalg.solve. And here we use a transpose. And then as the right-hand side, we use dj by dx transpose. So we will say del j by dx transpose. Let me bring this over a little bit more towards the right so that we see everything. And then we can plug it in. So we say plug in and get the sensitivities of the adjoint approach. So we get the dj by d theta in the adjoint approach. And for this one, we use this expression here. So the first one was the del j by d theta. So del j del theta plus, and then we say adjoint variable, and we need to transpose it and matrix multiply it with the dB by d theta. So dB by d theta. No, you don't see this. I will just bring it over here. And hopefully, if I haven't done any mistakes, we can just print out the sensitivity gradient that we got from the adjoint method. Then let's open the terminal and execute our Python file. I hope this should be fine. Okay, and here we get our sensitivities, and this is of course a three-dimensional row vector, and of course right now it's just a value that's standing there. Let's see how it works out for the other methods so that we can check whether the calculations are correct. Therefore, let's close the terminal here again, and I saw that maybe it makes more sense to give it the same number as we have in the PDF, so let's change this to 3 here. And as a next step, it would make sense to go with the forward sensitivity analysis, but I will rather do the finite differences, because this is also my advice to you. Whenever you implement adjoint methods, make sure that you also check them with the finite difference methods, because due to the fact that they can be a little bit confusing when deriving and implementing, there's a good chance that you did a mistake in the implementation. So you can then check your value against the finite differences. So I will do next up, step 1, finite differences. And for this, let me scroll up a bit to this one we have here. And the idea, as said, we will create an empty sensitivity gradient vector and then iterate over all the entries and compute them one by one. For this, let me first define an epsilon, which is 1.0 e minus 6 in our case here. I see this should of course be the minus 6, should be of course in the same line as the e here. This is 1.0 times 10 to the minus 6. So a number with 6 digits after the comma. And then we create our dj by d theta by the finite difference method. And for this, we will just use an empty container so far. So I will just pre-allocate this, and this will have the size 1 by 3. And then we can insert the values one by one. For this, let me now start a loop. I will do for I in range of 3, so that we iterate over all the 3 entries we have to calculate, and then create a b augmented, in our case the b tilde, and the b augmented will be first a copy of the b guess, and then we will augment the ith entry with the epsilon. So in essence, this will yield the same as if we would add the vector with the 0th or respectively the ith unit vector. And then we can solve the linear system again. So we do x augmented is np.linalg.solve of a and b augmented. And then we can create a j augmented, so an augmented loss function, or a loss function with the augmented x in it. And for this we say again 0.5 times x augmented times x r or ref transpose times x augmented minus x ref. And okay, let me bring this over a little bit so that you can see what I write here. And then we can evaluate the derivative by the help of finite differences in the way that we say dj by d theta finite difference at the ith point. But since we have a row vector, we just have to say 0 row and then the ith entry is equal to, and here we use j augmented minus j and divided by epsilon, the definition of a forward finite difference. Then let me move over the PDF again, and if we have calculated this, we can then print out the dj by the theta finite difference. And if I haven't done any mistake here, let's execute it again. And here we see we get also a row vector, and the entries up to the, I think it's the 6th digit after comma, are identical. We will later discuss why they are different. At least that's a good indicator so that we can now go on with the second method, the forward sensitivities. So I will use this point here and call it to the forward sensitivities. Okay, I hope you have. Okay, this is the forward adjoint method, or maybe let's call this the adjoint sensitivities. It's probably a little more concise. And since we will be using the same derivatives here, I will just copy them. And I copy them because later we also want to do some timing on how long these different methods take. Then by bringing over our PDF, we can look at the forward sensitivity method, and we see that the first step is to solve the batched linear system. So we want to solve not for one vector, but the Jacobian matrix or the solution sensitivities. So let's implement that. And for this, we first solve the forward adjoint system. I don't have a particular name for it. And out of this, we then get our dx by d theta. And we do numpy.linalg.solve again, and we solve system matrix A, and the right-hand side is the identity matrix, or if you recall, this was a db by d theta. So we plug in the db by d theta. And then we can have the next step, which will be just plug in. And if I scroll down, you see it works like this. And the way that we say the dj by d theta, and I will call this forward, will be first the del j by del theta, which is of course again 0. And then we have the del j by del x, del j by del x. And here, of course, we don't have to transpose it because the del j by dx is already the transposed vector. And we do a matrix multiply with the dx. I will just move it over. You probably have seen it now, by the dx by d theta. And then we also have our forward sensitivities. I will just print them out again. So dj by d theta forward. And then let's open up this one. And now don't be confused. The first entries is adjoint, second one forward, and the last one finite differences. And bam, we see also the forward is accurate up to the 6th digit. Now let me close this down, and I will quickly adjust the printing to make it a little bit more verbose. And here we are again, just some more verbose printing. And I also added a flag here to change the numpy precision to 16, which means it will print 16 digits after the comma. And here we go. So first of all, we see the loss function, which is not particularly interesting for us. We are more interested in the sensitivities. And now it will be, of course, a little bit eye-cluttering, but I hope you can still follow. If we compare the adjoint method with the forward method, we see that the loss gradient is identical. Whereas if we compare the both with the finite differences, we see that they are only close up to, let's say, the 6th digit after the comma. And the interesting aspect is that the forward and the adjoint method yield sensitivities that are exact up to machine precision. And we also see up to the 16th digit after the comma, they are identical. Whereas for the finite differences, we suffer from numerical rounding errors. This is an inherent problem with finite differences, and Therefore, we also chose the epsilon to be 1e minus 6, or maybe choose it 1e minus 5, 1e minus 4. It's a little bit, depends on the scenario, but this is an optimal value for still getting a good approximation to the gradient, but also having as little rounding errors as possible. And therefore we can only guarantee it is accurate up to the 6th digit after the comma. However, that is already sufficient in order to check whether our gradients are correct. So it doesn't matter how the last digits are, because here we already see that the calculations or the implementations of forward and adjoint method must be correct. And as a last interesting point, I already mentioned it, I will now implement some timings and I will also print them out. Okay, I implemented a printout of different timings in nanoseconds, which of course means that lower is better. And I see here I was missing the subtraction from the starting time. So minus time, finite differences. Let me also check if it's correct for the others. Yes, that should be fine. Then we can run it and see how long the different approaches take. And we have first the time for the adjoint, then by the forward, and then by the finite differences here. And what first impressions are, of course, the forward is the fastest, then the adjoint, and then the finite differences. Of course, we would have to run it a couple of times in order to get some sufficient statistics here. However, we probably see that the ranking almost stays the same here. It's interesting to see that the finite differences are the most expensive. That is probably due to the fact that we used a Python loop in here. Maybe if we would have vectorized these operations, then it would have also gotten faster. However, the bottom line is that for a lot of applications, especially then when we also look at nonlinear systems and ODEs, etc., the finite difference method will always be more time consuming. And on top of that, the gradient is not accurate or not accurate up to machine precision. And then something that you probably think is a little bit in contrast to what I advertised earlier, that the forward method is faster than the adjoint method. This is probably caused by the fact that we have such a small system here. In general, of course, especially then if you have a lot of parameters, the adjoint method will definitely be the faster approach. Because here we have as many parameters as we have unknowns, therefore there's kind of like this in the middle ground where both methods are living in the same order of magnitude. But however, as we also saw in the introduction to the adjoint method, that you should use the forward method when you have a lot of unknowns but only a handful of parameters, let's say 5 or 6, and you should use the adjoint method if you have way more parameters and even if your number of parameters exceed your number of unknowns. And with this, I'm at the end of the video. You will find the code as well as the PDF on GitHub. If you enjoyed the video, then please consider liking and subscribing. If there were any confusions throughout the way, then write a comment. I would be happy to help you. Here you will now see similar videos, and I hope to see you in the next video.